Hi guys, welcome to Learn Electronics Repair. Today we're going to talk about continuity mode, resistance mode and diode mode on multimeters. In particular, what's the difference and when and where should you use either? Okay, so let's start at the best place to start, the beginning, and let's just look at what really is the difference between using resistance mode or continuity mode with resistance and diode mode. And this comes down really to the fact there are two ways to measure a resistance. And that's because we have Ohm's law, which we'll put in the triangle: voltage, current, resistance. Now, the reason we put it in the triangle like this is because if we want to know how to calculate one, we put our finger over it and it shows us the formula. So voltage equals current times resistance. Current equals voltage divided by resistance. Resistance equals voltage divided by current. So according to this, there is only one way: resistance equals voltage divided by current to measure resistance. Yes, there's only one formula for that, but there isn't only one way, because you can do this physically, practically, in two different ways. You can either apply a constant voltage to the resistor and measure the current that flows through it. So this, you know what it is, and this you measure. Or you can pass a constant current through the resistance and measure the voltage across it. So in that case, this is the one you preset and this is the one you measure. So the two ways you can measure a resistor is either with a constant voltage, or a known voltage at least, or with a constant current. So now we know there are two ways to do that. Let's have a look at how our multimeter does it. Does it do it the same way with both diode mode and resistance mode? Does it do it different ways, and which way does it use? Well, let's have a look. Well, to do this, we're going to use three multimeters: volts, amps, which will be measured either microamps or milliamps, and resistance. So this is the meter I'm going to use to measure a resistance in normal resistance mode, continuity and diode mode. Okay, now I can zoom out and show you how all this lot is wired up with a big jumble of wires here, but it's going to be easier if I just draw this on paper first so you understand what we actually have here to test the resistance with. So here is how I've wired up my multimeters. Resistance, I can't fit the whole word in there, so I'll put res slash, I'll even draw the picture, res slash diode, diode mode. So from your minus and plus here, I'm connecting to a voltmeter. And I'll draw the terminals the other way around because it's easier, okay? So on here, plus, minus, here's my voltmeter. Which I can say easier than I can write, obviously. So now from the meter I'm measuring with, this is the measure, I need to connect my probes. So I have my black probe connected. It's connected together there. So this is my black probe. And the red probe I have connected from here, going to another multimeter. Plus minus, and this is current, and coming out here is my red probe. So when I connect my two probes together, for example, this should read 0 resistance, this should read 0 volts because I've shorted the wires together, and this should measure the current that's passing through the two probes. And the same when I connect a resistor across here, I can see what voltage is coming out of my test meter and what current is passing through the resistor. So let's look at some resistors first and let's see how the multimeter measures them. I have my fluke meter set to normal resistance mode. This is measuring volts, this is measuring the current, and I've set it to the microamps range. So you may be wondering why this meter on ohms range is reading about 10 mega ohms even though the probes are open circuit. Well, that's because this meter measuring the voltage is connected across this one, and this has an input impedance which is about 10 mega ohms. So what you're actually seeing on here is the input resistance of this meter. Now let me take a resistor. So this is a 10k resistor and we'll measure across it. Now you can see this is reading almost 10k and this is showing 0.107 volts. So that voltage is what's coming out of my meter on resistance range. Just go back on it again. 1.11 in fact, okay, that's reading 10 now. And on this one, the 11 microamps is the current that's flowing through this resistor. So this meter is measuring that current, 11 microamps. It knows its voltage because it's generating the voltage. And you can see that's, if you divide it yourself, that's how it comes to 10k. Yeah. You can see, although the decimal point, the digits are there. Okay. If we now take a 1k resistor and we do the same thing. Okay, 1k resistor, what happens? Well, this meter's still generating 0.1 volts basically, okay, 100th of a volt less, but very close. This is now passing 95 microamps, and this is reading just over 1k. So you can see that the meter is actually, in resistance mode, is a constant voltage source. The voltage generated stays the same, and it measures the current. Let's try a 10 ohm resistor. Well, the first thing you'll notice is it's reading 110 ohms. The reason for that is quite simple. This current meter has some resistance. The current is passing through a resistor inside here, and it measures the voltage across that resistor to give the current. And on the microamps range, it has about a 100 ohm resistor. So what we need to do is put this to the milliamps range, and we'll try again. We're now reading 10 ohms, okay, and you'll see the voltage has gone down to 0.003. So you can see that at very low resistances, this meter can no longer provide the constant voltage of 0.1. That's because at 0.1 volts through a 10 ohm resistor, it would have to pass about 100 milliamps, yeah, and it's not able to do that. So apart from very low resistances, this is a constant voltage generator. You'll also notice now that the voltage 0.003 is about the same as the current 0.3 milliamps. So that's how it's working. It is a constant voltage generator, but it can't do that into a short, for example, because a short is a short. Again, this is now reading 0 volts, 0.2 of an ohm, 0.2 of a milliamp. It's obviously not 0 volts because there is a little bit of current flowing. It's a little bit more than 0 volts. This is just not sensitive enough to tell me exactly what. Now let's have a look at continuity mode. So I'm just in continuity mode. I'm still in resistance, okay? We now get a bleep because I've switched the bleeper on, and this will measure up to about 40 ohms, it says, and bleep. So if we take our 10 ohm resistor again, connect it across our meter probes, you'll see we have the same sort of thing. It can't generate the 0.1 of a volt, but you'll see the voltage and the current in milliamps are relative to each other, and that's why we have 10 ohms. So once again, when you're in continuity mode, it can't actually generate the higher voltage because the current would be so high. So for low resistances, fair enough, it is generating the voltage and it knows what it is, but once you get to the higher resistances, you can see it's a constant voltage generator, and that will apply with much higher resistances as well. For example, here is a 100k resistor, and this will still generate about 0.1 of a volt. Let's go, you'll see. Yeah, 0.11 volt. We're back to that again. Constant voltage with 100k. So now we know resistance range works in constant voltage mode, and the same applies to the bleeper or continuity mode. What about the diode mode? Well, let's try it. I'm now in diode mode or semiconductor junction testing mode. And you can see this is no longer reading ohms. This is reading volts DC. I'll go back to the milliamps range to make sure there's no resistance in this. And you can see now the meter is generating 2.97 volts. So it's not 0.1 anymore. It's nearly 3 volts. And this is enough voltage to turn on a semiconductor junction. That's why diodes, although they effectively conduct, they're like a short in one direction, don't show up on the resistance range, because 0.1 volts is not enough to turn on the diode or transistor junction. Let's short the leads together. And you will see the meter is now generating basically 0 volts or very close to it. Okay. You see it on there acting like it's just telling us effectively just short, 0 volts. And it's passing about 600, 700 microamps. Yeah, 0.6, 0.7 milliamps into the short. So that's the current going into the short. Let's look at a normal rectifier diode. Blips ones. And you'll see 0.5 milliamps, 0.6 milliamps. So the current is very similar to what we had in the short, and this is measuring the voltage across the diode. Let's take a Schottky diode. This will read lower, 0.154, but you'll see the current is getting about 5 milliamps. It's basically the same current, 0.6 there. So you can see now that in diode mode, your meter is acting as a constant current source. And that is the major difference between taking measurements in both ranges, or both modes, I should say. Yeah, one is a constant voltage source with too low a voltage to turn on a semiconductor junction. The other one can turn on a semiconductor junction, and because you need to limit the current flowing through that junction, otherwise you'll just burn it out, it is a constant current source. Okay, hope that was clear, because that will be useful to us in the next part. Let's look at testing some components in diode mode with the component out of circuit. Let's just start with the most simple things then. So this is a rectifier diode, silicon diode, and we put the meter probe across with the black lead to the stripe. So this is the positive one, the red, to the anode, and it conducts. And we can see the voltage drop there across the diode, 0.511. And if we reverse it, this will not conduct. So that is a good diode. If it reads open in both directions or short, which will be in both directions, then it's a faulty diode. This is a Schottky diode. You can see the symbol on it here. So this is the anode. If we put the black lead to the anode, it will not conduct. And with the red lead to the anode, it will conduct, but we'll get a lower voltage drop, 0.15. So that is a Schottky diode. And that's how you can tell the difference between the two. You will also find some fast switching rectifier diodes that read around 0.4 volts. Here is one. This is a HER503 5 amp fast switching diode, and you can see 0.417. So you can tell by the voltage drop the difference between a normal silicon rectifier, a fast switching diode, or a Schottky diode. Another type of diode you may come across, this is a germanium diode. You'll probably only find these in radio frequency circuits, and if we look at this one, 0.28. So depending on the type of diode, you will get a different reading. We can also test LEDs in diode mode, and the voltage drop will depend on the colour, basically, of the LED. One direction they will read open, and one direction they will conduct, and they will light up. So I think you can see this one here is a red LED reading 1.7. If we reverse the polarity, it doesn't light up and it reads open. So 1.7, 1.8, typical for a red LED. Here we have a yellow LED. Same thing, it will light up in one direction with the positive lead or the red lead to the cathode. You see that's not lighting up, it's not conducting. And that's a yellow one, so you can see it lighting up there, yellow against the background. And that's reading about the same as the red, 1.78. Here we have a green one. Let's try again. So clearly lighting up, and we can see the voltage drop is higher on this one, 2.23, 2.24. You'll notice normally with LEDs, by the way, if they are new ones, the longer lead is the positive, if you like, and that inside the LED is like a small terminal. You see, and here we have a small and a large hoof, if you like, the small one being the positive, at least on the red, yellow and green ones. May not be so on the other ones. But we can see that 2.23. Now to a blue LED, again the longer lead here being the positive, and it's like the small terminal inside it. Okay, so we check this one. Lights up blue, you can see, but this one is actually not reading on my meter. The voltage drop is up very close to the maximum reading on diode mode. Okay, on some multimeters it will read. And try this one. Yeah, 2.54, you can see it there on that one. And we can also try a white LED. Again, you'll notice the long lead, there's a smaller terminal inside it, which is the anodes, the positive end. Let's see if this one lights up on my fluke meter. It does light up but doesn't read. Okay, we'll try it on the aneng as well. And that reads 2.6. You can get ultraviolet LEDs, but I'll tell you now they read the same as the white ones, because a white LED is just an ultraviolet LED with a fluorescent coating, which is what makes it glow white. You can get infrared LEDs also. This one is a pull, but I know that the anode will be the one with a small terminal inside it. So we can put our positive lead to it, and let's measure this one. And that reads 1 volt. Okay, so that's an infrared LED. We can't see it lighting up, but we can assume it is. I guess if we pointed my phone at it with a camera, we'll probably see it lighting up, but that is an infrared LED. We'll just measure the other way. Should read open if it's a good one. Yes, it reads open. Another common type of diode, or if you like a diode matrix really, is a bridge rectifier. These come in a whole variety of shapes and sizes, from small surface mount ones to big chunky ones like this, but they basically all test the same way. You will see we have a positive terminal, a negative terminal, and then 2 AC terminals. The pinout doesn't have to be the same as this, but this is a very common one. So if we apply a positive voltage, which is the red lead in diode mode, to either of the AC, it should conduct in the direction of the positive end of the bridge rectifier. If we apply a negative voltage to either of these, it won't conduct in this direction, but it will conduct in that direction. So with a red lead on either of these, we should see a diode junction to positive. reverse direction will be open. With the black lead negative onto either of these, we'll see a diode junction to that one. Opposite will be open. So let's look at that. So red lead AC to here should see a diode. Yeah, 0.53. We know that's a silicone diode from the voltages we were just looking at. And from this one, the same. Okay. If we put the negative, the black, onto here, we should see a connection to this end, to negative. Black to negative, remember that. Black to negative. Now, if we go the opposite way round, we won't see a direction here. So we will get both feeding to there with that and the AC, but neither connect to here. Okay, and the same applies with the red. We've already seen with the red on either of these, it conducts to this end, but it doesn't conduct to that end. Okay, that's a good bridge rectifier. One other thing we can test is between the two AC. We shouldn't see anything, should be open. And between the plus and minus depends on which way you put them round. Normally speaking, in circuit, this is the positive end. The AC comes in and this is your positive voltage rail. So this end, when this thing is working, will have the positive voltage. And if we put our red lead to its positive and go to negative, it reads open circuit. Okay? But if we put the black lead to the positive, which will never occur in normal circuit operation, and we go here, we'll see two diode junctions, or thereabouts, 0.98. Okay? Now that situation will not occur in normal operation. Okay? That will not occur. If you read a short across these, you have a short on the output. Yeah? So just bear in mind, if you wonder what that funny reading is, think, where is the black lead? It's on the positive. Okay, this situation will not occur when the circuit is operating normally, so you can ignore that. And that's another important point which will come in later when we look at testing components in circuit. Okay, while we're still looking at components out of circuit, let's look at some transistors and MOSFETs. Here we have some transistors. This is a TIP41 NPN power transistor. This package is called TO220 or TO220. That's the name of the package, and you find many transistors in this package. And the other one is this one, TIP3055. I can't recall the name of this package, but it's a common one. Usually with power transistors and these types of packages, the pins go base, collector, emitter, alphabetical order, BCE, and that's normal for these. Here is a smaller transistor. This is BC337. This package is called TO92, and again, it's very common. Now, whereas these pretty much always you know the pin out, with these you don't. This package is using every possible combinations of pin out you could imagine for different types of transistor. So let's look at these two, because we know which are base, collector and emitter, and see how they read. And let's see if we can work out the pin out of this transistor. Of course, I could have looked up this package name, but I'll wait for one of you guys to tell me. You should have known that. Okay, so this one, base, collector, emitter. This one, base, collector, emitter. That's almost always the case. When I say almost always, yeah, one day something will come and bite you on the bum because you didn't realise. Okay, but we can always figure it out. So on diode mode, a transistor basically looks like two diodes connected together. You can't make a transistor using two diodes, but this is how it looks. So for an NPN transistor, it looks like that. Base, collector, emitter. Okay, Let's measure it. So if it's going to read like 2 diodes and we put the red lead here, positive on an NPN, I'll make you note this is NPN, then we should see a diode junction to both the other legs. These two should read open. Okay, so let's try it. So positive on the base, collector reads 0.603, emitter 0.605. Okay, 0.603, 0.605. If we go in the reverse direction with the black to here, these shouldn't conduct, so we'd expect these to read open. We proved that with diodes a few minutes ago, so it's no surprise. That reads open and that reads open. You'd expect between the collector and the emitter to read open in both directions, because whichever way we've got one forward and one reverse bias diode. So that should read open, and this should read open. So that's a good transistor. Let's look at the other one. So this is another NPN, and the pin out should be the same as this one. So red to the base, collector 0.556. So you see it reads different from the other one. Similar ballpark, but not the same. 0.556, 0.567, 0.556, 0.567. Again, we reverse the polarity. Should read open both ways. Open, open. And between these two, should read open in both directions. So good transistor, NPN. Notice how the reading on the base emitter is higher than on the base collector. In this case, quite obviously so. In this case, it is higher. That is no fluke. This is a fluke. Okay, but that is no fluke. It's because of the level of doping in the silicone inside the transistor. The base emitter will always read higher than the base collector, and that's how you can tell which is the emitter and which is the collector. Okay, sometimes they will read the same on some transistors and you can't tell the difference, but unless somebody tells me in the comments below, you will not find a NPN transistor where the base collector reads higher than the base emitter. So you may find them both the same and not know which is which, but almost always you'll find the base emitter voltage is higher. Now we know that, let's look at this one. So again, we have 3 pins, but we don't know which is which. Let's start assuming that this one is the base. From here to here, with the positive on here, I'm not going to do it like that, guys. I'm going to have to do it this way. So from here to here, positive on the base, if it is the base, nothing. To there, nothing. So either this is a PNP transistor, opposite polarity, or it's open circuit, or this isn't the base. Let's try it the other way. From here to here, we have a junction. Okay, from here to here, it's 0.649. How about from here? From here to here, no. So it's possible this is the base, this is the red lead. It's possible this is NPN and this is the base. And the way to find out, this is the pin we think is the base in the middle. Do we see anything to the other end? Yes. So 646, 648. So firstly, we know this is NPN. Secondly, we know the middle pin is the base. And we know this is the higher reading, which is the emitter. So put it that way round. We have base in the middle, emitter here, collector here, and this one is reading 0.648, and this was reading 0.646. Okay, so you can see with diode mode on a multimeter, you don't need a component analyzer. You can tell whether that is PNP or NPN and which pin is which, almost always. A PNP transistor will read the same, but the opposite polarity. So let's try some PNP transistors, just to prove it. Here are some PNP transistors, a power transistor, a small one, again TO220, TO92 packages. With a PNP transistor, it looks like an NPN but back to front. So effectively this looks like two diodes connected together like this. Collector, base, sorry, collector, emitter, base. Because this is the TO220, we can almost certainly say the pins are B, C, E in alphabetical order, and this one could be anything again. So let's look at this. So we can think logically. If we put the black lead here or here and the red here, the diode is reverse biased, so this should read open. This is the direction where the NPN read like a diode, and it reads open, it reads open. Okay, if we put the red lead to this end of the diode, it will conduct, so this should read a diode junction, and one should be a different voltage to the other. 0.572, 0.570. Okay, emitter is slightly higher. And the polarity is the opposite, so this is a PNP. The way I normally remember them without thinking about it, by the way, I think NPN, and the P is the middle letter, and it's like the middle of the two junctions. If you put your positive lead onto the base on an NPN, P for positive, consider that the base, the middle junction, okay, NPN, positive on the base, it should conduct. If you put the black lead on a PNP, and I realise I've written B there, okay, if you put the black lead on the base, PNP, black negative, N, it should conduct. Okay? You remember the mnemonic whichever way you want to remember it, but that's the way I remember it. So, negative on the base, and it conducts, we know. Okay, again, between the collector emitter should be nothing in either direction. Let's have a look at this one then, see if we can figure this out. So we'll measure this the same way we just did the NPN transistor, and the base was in the middle. So we'll connect the red lead to the middle. What do we get? Well, there's no connection to there and there's no connection to there. So either this is not a NPN transistor or this isn't the base. Let's put the black lead in the middle. What do we have now? Well, we have a junction 683, and this one 685, slightly higher. So this looks like it's PNP because I have the black lead on the base, and 685.683. So this looks like this is the emitter, this is the collector, and this is the base. If that's true, then between the two outer ones I should find no conduction in either direction. Okay, so we go from here to here, nothing, of here to here, nothing. So we've identified that one, PNP. We know the collector, emitter and base terminals from the voltage. We'll have a look at some surface mount transistors in a moment, but let's have a look at some through-hole MOSFETs first. Here is a N-channel MOSFET, 18N50, common power MOSFET N channel. Let's just draw the symbol of this first so we can understand what readings we're going to see. With an N channel MOSFET, and this is a enhancement MOSFET, which is the common type. I'm not going to play around with depletion MOSFETs on this video, but we can make a video all about that. But we can make a video all about MOSFETs. In fact, I think I may have already done that. Actually, I'm pretty sure I did already do that. So this is your MOSFET, drain, source, gate. With this type, again, this pin, which was always the base on the transistors, or almost always, is almost always the gate on a MOSFET. Now, the symbol for the MOSFET is a little bit complicated. If you draw the full symbol, I tend to draw a kind of like a not quite full version of it. But basically what you see is, when you measure a MOSFET from the source to the drain, there is something called a parasitic diode. Now, on an N channel, the parasitic diode is like so. This is not a diode that they put inside the MOSFET. This is a byproduct of what makes up the MOSFET, the semiconductor junctions. Now, with an N channel MOSFET, this end, the drain, this is what goes to the positive supply, and the source goes to ground or powers a load, or the load is in here. Okay, some sort of load. And this is the source is the negative end, or ground. So if you look at this, it's reverse biased. In normal circuit operation, this diode does not conduct. It's in the wrong polarity. Some people think this is there to stop back EMF when you're switching coils. No, it's nothing like that. And in fact, it's in the wrong place. If this was a coil, your diode that effectively protects against back EMF is there. If you don't know what back EMF is, go and watch my video. All you need to know about inductors to fix stuff. Okay. So this parasitic diode does not conduct a normal operation, but we can see it with our multimeter. Let's have a look at this MOSFET. Pin out is gate, drain, source, or it could be gate, source, drain, but the gate will almost always be this side. Let's see. If this is the source and this is the drain, and it's an N channel, from here to here we should see this diode junction. And we do see it, okay? From there to there, all the way we see nothing. If you go from the gate to either of these, drain or source, in either polarity, you won't see anything. Because the gate is effectively open circuit on the MOSFET. There's no current path here. The only thing you see is that one. And if you see it with the red on the source, you can look at the data sheet to be sure, that is an N channel MOSFET. Now, you've noticed when I come to measure it again, it reads different. Why? Well, let me show you. If I put my black lead on the gate, red lead on the source, I'm putting a negative voltage on here compared to here, I'm turning this MOSFET off. Okay? And what I see now is the parasitic diode and nothing the other way. If I put my red lead on the gate, I'm putting a positive voltage on the gate, and that turns the MOSFET on. Now, this gate acts like a capacitor, so it charges up. And when I take my meter probe off there, it remains charged, okay? And that means the MOSFET stays turned on. Look. See? Conducting both ways. I'll go again, just get some charge into the gate. It's turned on. It's turned on fully in that direction. So I've turned the MOSFET on by putting my positive read on the gate. If I put the negative one on there to discharge it, it turns off again, and I just see the diode. You see the difference? Switch it on. and it's now a short. Switch is off, and it's now a diode. Okay, that's how you test a MOSFET with a multimeter, and you can actually test that it will switch on and off. When it's switched on, it will conduct in both directions between the drain and source. When it's switched off, you only see the parasitic diode. You can't do that in circuit, by the way, because there's resistors connected from the gate to ground, a pull down resistor to stop the gate from floating and turning on just by stray electrical current or voltage. If you can do that in circuit, there's something wrong with the gate drive circuit. It's floating. Okay, let's look at a P channel. Here is a P channel. I don't have any through hole, but this is a P channel surface mount. So let's use this. So one of the pins, I'm not sure which one, will be the gate, but whichever is the gate, it'll be one of the corners. We'll have 3 pins which are drain and 4 which are source, or vice versa, 4 drain or 3 source. So if we go across some of the middle pins, we know we're not on the gate. Let's have a look. So that doesn't conduct, there's no parasitic diode there, okay? Let's go the other way. And we see the parasitic diode. If we know this is a P channel, then we know the diode is reverse biased. So the positive lead is on the drain. Do all these 4 read the same? Yes, 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 yes. So those 4 are all connected together. One of these 2 ends now will be the gate. So if we touch that one with a positive, does anything happen? No, it's still reading the same. Touch this end with a positive. So that is actually part of this, all these 3 connected together. So this one, which doesn't read, this is the gate. But putting the positive on the gate doesn't do anything. Let's put the negative on the gate. Okay, let's put the negative on the gate. So from here to here. Now does it read anything? It should conduct now. Yes, it conducts because we've switched it on. And we switched it on by putting the negative on the gate. So this is definitely a P channel, we know that. It'll read short in both directions now. And it'll keep on doing that till we put the positive on the gate. And then it goes back to being switched off. So we know the negative switched it on. We know it's a P channel MOSFET because you put a negative voltage or a 0 voltage on the gate compared to the source to switch it on. So we know what it is. So that's how we measure those. Here's an N channel MOSFET. It's the opposite way round. You'll see it. This is a little bit easier because these, like the power transistors, this pin is pretty much always the gate. So we can say drain source, we see a parasitic diode with a negative here, positive here, okay? All the way around, nothing. Try to switch it on with a negative lead, it shouldn't do anything. If it's N channel, doesn't do anything. Try to switch it on with a positive on the gate. Switch is on. It's now short. So we put the positive on the gate to switch it on. This is an N channel MOSFET. And we know this is a gate. We knew that anyway. We know it's a good one. So that's how we test MOSFETs out of circuit. We'll move on to in-circuit testing. But just before we do that, I want to just show you how to test transistors out of circuit, the surface mount ones, because this is where you can become quite confused. Here we have some very common NPN surface mount transistors. This is 1AM as the SMD code. It's very common. And we can see with these type of transistors that this pin, the one that is now stuck to my probe, is almost always the base or the gate. This could be a bipolar transistor in this package. It could be a MOSFET. Let's have a look at it. If this is the base and it's NPN, Okay, that should stay in place. Let's try it. Base, collector, normal. 0.608. This should be the emitter. Should read a little bit higher. 645, quite a bit higher. Okay. So that is an NPN transistor. Now, what may confuse you? You may find things that look like this that measure like a transistor if this was the base, but they don't make transistors like this where this is the base, at least not that I know of. Of course they probably do, just to confuse matters even further, but I'll show you why you're going to find things that look like this, transistors, that read where the base is here. And the reason is because of these things. So these are diode matrices. You can see the package is exactly the same. SOT23, small outline transistor, 2.3, which is 2mm by 3mm. That's why it's called that. These are quite often marked in strange ways. L4P, L43, you can see here some markings. WW1 and WV1 I've also seen from different manufacturers. And inside here is not a transistor or a MOSFET, but two diodes. And they come in variations. So this one, and this is Schottky diodes in this one. So these will read about 0.15 volts between the diode junctions, but you can get these in normal silicon diodes as well that read the same as the transistor junction. There is a variant here, BAT54, and there's plenty of similar devices that is just a diode. If you read this in circuit or even out of circuit, it may look like a MOSFET, with this being the drain or source either way, depending on whether it's P channel or N channel. But the gate, which would be over here, will not switch it on or off because there's no connection to there. Also, the gate is here normally, okay? These two will look like an NPN and a PNP transistor. So this one will look like the base is here, and if you put your red lead here, it will conduct to both of these, and it will look like an NPN transistor. Same with this one. If you put your black lead here and the middle pin, it will look like a PNP transistor. And this one is just going to look strange because you have a diode junction in one, a diode junction in the other direction. You won't be able to make any sense of what that is supposed to be. BAT54A, common anode, 54C, common cathode, 54S. So watch out for these. If you think that pin 3 is the base, you've almost certainly got a diode matrix. The other giveaway is both these diodes will read identical, so you will not find the emitter slightly higher than the collector. So just take a bit of care with that. In circuit, usually, but depends on the board, if they put the silkscreen markings, this will be called D followed by some number, D10, D21, whatever, rather than Q10, Q21, Q being a transistor, either bipolar or MOSFET. So watch out for those guys. They will confuse you in circuits and you think you got faults you haven't. And even when you take the thing out, you'll still think it's faulty, possibly, or you will not realize it's a diode matrix. Okay, just thought I'd mention that. Now we've talked about some of the things that can fool you with this. Let's have a look at in-circuit testing and look at the other things that can fool you with this.